Okay, hi everyone. M1 video. So, this is kind of the first video on force diagrams. I just want to reiterate that everything in M1 is going to seem quite difficult and abstract at first, and that's because you've never seen anything like it before. You've never done anything at school like this. So, don't worry about it. Just have patience. It will come through. You will understand this stuff. You just got to have faith, follow the videos, follow the work, and you will get there, okay? And you can watch this video as many times as you want, of course. Now, what the purpose of these force diagrams are is, like, for instance, if I said I want you to push a block and it's against a rough surface and there's a string pulling it as well, how do you kind of draw this stuff? How do you mathematically work out, well, what is the force on that string and what is the frictional force? What would the acceleration be in that situation? And that's what we're going to deal with here, okay? So, first off, we need to uh, look over these Newton's laws of motion. Really important and sets up the fundamentals behind pretty much all of M1 and a lot of M2 as well, okay? And in particular, Newton's second and third law is going to be used all the time. Now let's look at this first law then. So it's saying in an inertial reference frame, that's just a really posh way of saying in space really, where nothing is prone to change. So in an environment with no external forces, the environment itself is not going to change. So free space, you could say. An object either remains at rest or continues to move at a constant velocity unless acted upon by a net force. So just think about an object floating in space. Okay, that object floating in space, this law is saying that that thing will continue to float at whatever speed it started with. Okay, it would just float on, float on, float on forever, unless an external force went, no, actually, I want you to stop, and it acted on that particle and it just stopped. And again, if it just stops, nothing will change it from stopping. It would just stay suspended where it is, unless I applied a force even bigger that it starts to move in the opposite direction. Okay? So in other words, this is what we mean by equilibrium. Okay? And equilibrium is a really important concept to be referencing all the time, which means an absence of acceleration. Okay, so it's saying that unless a force interacts with the object, it will stay in equilibrium, i.e. it will not accelerate, it will just stay moving at a constant pace, or it would stay still, okay? Or if a force does act on it, it will just continue to accelerate forever, and therefore it would not be in equilibrium, okay? So equilibrium means there is no acceleration. It does not necessarily mean that the object is stationary. Law number 2, in an inertial frame, the vector sum of forces is F equals ma. So F equals ma, where F is what's called the resultant force. So that's taking into account, let's say, all forces going left and right, which force wins? In other words, which force is most powerful? The sum of all the forces to the right or the ones to the left? And if the ones to the right are more powerful, then it's going to accelerate towards the right, let's say. So our m is the mass and a is our acceleration. Okay? And we'll be using that formula to resolve forces all the time. And resolving forces means finding missing forces. Law number 3, when one body exerts a force on another, the other body simultaneously exerts a force in equal magnitude and in opposite direction on the first body. That's very apparent if I rested a book on a table, for instance. The book has a weight, a corresponding weight, doesn't it? Which is the same as the mass times the gravitational constant g. Now g is 9.8 meters per second squared in maths, not 9.81 as it is in physics, okay? It's 9.8 in maths. If you use 9.81, it's -1 every time, okay? So, what is this g? Well, that's your gravitational force which is acted on by the Earth. So how does that work? And what is this? Well, let's go back to this weight. Okay, so the weight equals mg, so your mass times the gravitational constant. This thing would just fall through the table unless the table exerted an equal force in an opposite direction to prevent it falling through, prevent it breaking the table. And this is called the normal reaction. Okay? The normal reaction, if you look at this particle on the table, it's like a circle, isn't it? So that table is a tangent to the circle, and the force that comes out is always normal to the point of contact from the surface. So there's the point of contact there, and your resultant force, your R force, is coming up to oppose it. Okay? So your resultant force is 0. But let's just forget the resultant force. This is your normal reaction, which we call R. Okay? And why does G always go down? Why does gravity or weight always go down? Well, because think about it, the world, you can model it as a giant circle. If you're standing on a bit of land, okay, that's your little tangent to the circle, and the normal to your tangent always goes through the center. So it's always, wherever you look, going to point down towards the center of the Earth, right? So the normal reaction prevents that particle going through the table and just falling and crashing on endlessly towards the Earth, okay? So normal reaction is always perpendicular to the surface, or to the point of contact with that surface. So let's do some real examples then, and you'll see what I'm talking about. So I've got a particle of mass 5 kilograms pulled along a rough slope. So why do we measure it as a particle? Well, a particle has all of its center of mass centered at one point. So let's imagine, I don't know, you've got a big bear. Big bear, teeth, yeah. I actually really like bears. Anyway, big belly. Okay? Right, let's say we got a bear. That bear, if I was to do modeling with him, and that doesn't mean on the catwalk, if I was going to model a scenario with him, I don't know, like throw him in the air, drag him, push him, whatever, this thing is going to be subject to air resistance and movement around of flesh and all this kind of stuff, which is really complex to model. So what we'll do is we'll center all that mass into a single point. And in theory, you should be able to hold the bear by that point there, let's say by a piece of string, suspend him up there, and he would remain flat, remain balanced, because all of the mass is equally distributed around that point. So particles are how we model all bodies at the moment until kind of M2. So particle of mass 5 kilograms, so there's our weight straight away, 5g. Remember, it's resting on a table, horizontal, so therefore it has to have this normal reaction force, otherwise it would just keep falling through the table. It's being pulled along a rough, so as soon as you hear rough, that should make you think, oh, there's friction in there, by a horizontal force of 20 newtons. So there's 20 newtons, and the frictional force has magnitude 4 newtons. So friction, Fr, is always going to act in the opposite direction of the intended movement, 4 newtons. Now, if you're being pulled 20 to the right and only 4 is resisting on the left, then therefore you're going to be moving right, but not only moving, you're going to be accelerating to the right because the forces are greater on the right-hand side, right? So there is acceleration, and therefore this is not in equilibrium, okay? Which, remember, means an absence of acceleration. So there's the force diagram done. Now we can go to that Newton's second law and start finding these missing forces. So if I resolve to the right, that means I'm considering all forces to the right. And in the end, all forces need to be considered in your diagram, and then you're finished, okay? So all the forces to the right are this 20 newtons, and we always resolve in the direction of motion normally, or in the direction of acceleration, whichever. But everything is relative to the right. So everything that is moving right is positive. Everything which is moving left is negative. And remember, this is F equals ma, where F is the net resultant force. So 20 to the right, 4 to the left equals our mass, which is 5, times our acceleration, we don't know. So A is 20 minus 4, that's 16, all over 5, which is 3.2 meters per second squared. There we go, that's done. And also, we might as well find out what this R is. So if we resolve up and down, if I resolve up, the force going up is R. The force going down in the opposite direction is 5g, which is, remember, 5 times 9.8. No other forces going up and down, so equals. And then you've got your mass times acceleration. The mass is 5. The acceleration, though, it's not accelerating up and down. It's not bouncing up and down, is it? So acceleration is 0. So therefore, R must be 5g. So that's 5 times 9.8. 5 times 9.8 is 49 newtons to 2SF, which we have to write every time because G is to 2SF. So all answers to either 2SF, sig fig, or 3SF. If you do any more, you lose a mark every time. Let's go for another example. So a particle of mass 7 kg, is being pulled along a rough table. Okay, so here we go. Particle 7g must have a normal reaction because it's touching a surface. Rough table, so therefore there's friction involved. There's a string, which is magnitude 50 newtons, 30 degrees to the horizontal, and there's friction. Now friction, the formula for friction is mu r, where mu is the coefficient of friction and r is our normal reaction, okay, which we've already labeled. Coefficient of friction basically describes a ratio or a scoring of the interaction between two surfaces. So between two different surfaces or materials, once they interact, that has a corresponding frictional component, frictional coefficient, and you'll either have to find that coefficient or you'll be given it, and then you can use that to find something else. So let's do what we did before. We're trying to find the unknown forces. So Newton law 2, which F equals ma. We're going to resolve to the right first, like before, because it says it's in equilibrium. We know that A equals 0. Remember, there's no acceleration. So we resolve to the right. What forces are going right? Actually, no. Let's resolve up and down first. Yeah, let's resolve up and down. So it doesn't matter which we do, but we'll go up and down first. So what forces are going up and down? We've got R, but also we've got this string, don't we? Even though it's off at an angle, that string has two components, doesn't it? It has a bit moving, trying to force this thing to the right, and it also has this thing trying to force it upwards, doesn't it? Imagine it as two strings acting on this point here. Some of it's pulling it to the right and some of it's pulling it up. That's the same effect, isn't it, as this diagonal pull by the string. So how do we deal with that? Because we are only going to split this up into up and down and left and right. Well, it's easy. If I draw that triangle again, here's 30 degrees, here's 50, here's x and y. We know through SOHCAHTOA that cos 30 equals adjacent over hypotenuse, so x over 50. So therefore x would equal 50 cos 30, right? So this is 50 cos 30. We know that y for SOHCAHTOA, sine 30 equals y over 50. So therefore y would equal 50 sine 30. Okay? So notice what's called component. So these dotted lines are called components of the force. So if I say to you, I'll just split the force up into components. That's what I mean. Split it up into its up and down, left and right elements, or however you want to split it, right? Because remember, we have to account for all forces. And the reason I'm splitting it up in the first place is that we have nothing to compare this uh, this to unless we put it in comparison to all the other forces, right? So now we can almost disregard the diagonal force and we can just look at things being left and right. Now, we wouldn't normally draw this arrow here. We normally draw arrows coming out of the particle. So I'll put the 50 sine 30 here, but that was just to show you through the triangle what was happening. So just remember the side next to the angle is going to be your cos and the other one's going to be sine, right? So if we resolve up, we have r, which we've described. And now we've got this plus 50 sine 30. Subtract all the other forces going down, so that's 7g. It told us it's in equilibrium, so no acceleration. So therefore r equals 7g. Subtract 50 sine 30, which equals, so we got 7 times 9.8 minus 50 times sine 30, which is 43.6 newtons, right? So that's our R. And because we've used G, that's still to 3SF, remember? And now we'll resolve to the right to try and find out what this mu is, right? So if the question was find the coefficient of friction, we can do that. So the force is to the right, 50 cos 30, that's our component right there. And then we've got our minus mu r, which goes to the left, and there are no other forces, equals ma, which we know is 0 because it's in equilibrium. So therefore, to find mu, we would have 50 cos 30 divided by r, that's just move that over there and divided by r, which is going to be 50 cos 30 over 43.6. And that equals, so 50 cos 30 divided by 43.6, 0.99323SF. And there's our value of mu. Okay, cool. Next example. So this time, we've got a particle of mass 6g, 6 kilograms, being pushed up by a force of magnitude 100 along a rough slope. Okay, so here's a slope. It's saying the slope is elevated at 20 degrees to the horizontal. Now we start getting into the difficult, well, escalating in difficulty. Okay, here's our particle, 6g. Remember, the weight always acts down. And again, if it wasn't a normal reaction, it would just fall through the slope. And remember, the normal reaction is always perpendicular to the surface, okay? To the surface, right? It's saying it's pulled up by a force, pushed up by 100 newtons, so up the slope, and it's a rough slope. So therefore, we know friction is always going to oppose its motion, and the motion is going up that slope. The particle is initially at rest, okay, and it's not in equilibrium. Okay, I haven't written that, but it's also not in equilibrium, so it is accelerating. Okay, and let's say it's accelerating with a equals 3 meters per second squared. Okay, so that way the question could be find mu r, but until we do that, I want us to get in this habit of splitting it up into components again. So you notice that the majority of forces are left and right this way, so diagonally, and this is 90 degrees. So already we've got 3 forces which are in line with each other or 90 degrees with each other, and therefore this force has to be split into components to make it match, because remember, all coordinates, all forces need to be considered. And this is what I mean by resolving parallel and perpendicular to the slope. These two forces are parallel to the slope. So Newton's second law, resolve parallel to the slope. Notice the diagonal this time. The force going up is 100 newtons, so in that direction. This force must be split into components, so I make sure I've got everything. So dotted line for component, 20 degrees. Remember, this would be like a triangle like this, yeah, to make that 90-degree triangle. So therefore this is next to 20. So this is going to be the hypotenuse 6g cos 20 from that SOHCAHTOA stuff. Likewise, we wouldn't put that force down here. We would put the force along the slope. So 6g sine 20. So it's always cos and sine, right? And now we can finish our thing. So force going up, 100 newtons. That's the only force going that way. There are two forces going in the opposite direction. So minus 6g sine 20 and minus mu r, yeah? Equals the mass times acceleration. So F equals ma. The acceleration, we're told, is 3 meters per second. So this is mass 6 times 3. We're trying to find mu, so we also need r then. So if I rearrange at the moment, I've got 100 minus 18, that's your 18, minus just 6g sine 20 equals mu r. So just move that over, move that over. So divide everything by r, and you get mu. I need to know what r is then to find mu. So this time I'll resolve perpendicular to the slope. Right? So this one was parallel to the slope, and this one is perpendicular to the slope. So now, the force going perpendicular to the slope is r. Are there any forces going up? No. Are there forces opposing it? Yes, this component here. So minus 6g cos 20 equals mass times acceleration. It's not accelerating up and down like that, is it? It's not bouncing up and down on the slope in a perpendicular fashion, so it's 0. So therefore r equals 6g cos 20. Okay. So therefore mu equals 100 minus 18 minus 6g sine 20 all over 6g cos 20, which will be 100, so 100 minus 18 minus 6 times 9.8 times sine 20 all divided by 6 times 9.8 times cos 20. So 1.12, which, because I made up the numbers, and this is the free SF, remember, that is way too high. So when you get a mu above 1, you're probably not right. But because I made the numbers, you know, like you can have mu above 1, but it's so rare, you've probably made a mistake. Okay? So I did just make that up, these values. So really, the theory is all there for you, and that should be all right.